Today we have a very interesting problem. To solve this problem, we need to know some properties of medians, angle bisectors, altitude, and more. We have a triangle ABC. We know two sides of this triangle. Side AB is 2 squared of 3. Side AC is 2. In this triangle, we draw a median, BD, and we know the length of this median is square root of 7. We draw an angle bisector, CE. Point F is point of interception of BD and CE. We also draw another line, GH, that goes through point F, and also an angle bisector of an angle EFB. And we ask to find the areas of the yellow triangle and the green triangle. In the previous video, I was talking about Stewart's theorem. Just to remind you, Stewart's theorem relates 5 lengths. So if I have a triangle ABC and I have a segment BD inside, I have 5 lengths A, B, C, D, and E. And Stewart's theorem gives us an expression that relates all these 5 lengths. The expression is quite complicated, but if you didn't see the previous video, I highly recommend you to watch it, because the video not just talks about the Stewart theorem itself, but also tells you how you can use it without actually memorizing it. And I also mentioned there are a couple special cases of a Stewart theorem. And one case is when BD is a median. In this case, Stewart theorem becomes much more simple expression, which is called Apollonius theorem. So Apollonius theorem in our case would mean this expression. And if you notice, we know everything here except for BC. So we can use Apollonius theorem to find BC, which equals to 2. Now notice that BC is actually equals to AC in our case. So our triangle ABC is an isosceles triangle. And CE in this case is angle bisector, but it's also going to be a median. So AE will be equal to EB and equals to square root of 3. And also CE will be in altitude. Since CE is a median, and BD we know is a median, that means that point F is a point of intersection of the medians, which is called centroid. And we know that centroid splits medians with the ratio 2 to 1. What it means is that BF will be 2/3 of BD, and DF will be 1/3 of BD. In a similar manner, CF will be 2/3 of CE, and EF will be 1/3 of CE. We would find CF and EF if we find CE, but that's really easy to do. If you look at triangle AEC, it's a right triangle. We know two sides of this triangle, so we can apply Pythagorean theorem to find CE. CE is 1 in this case. And because of that, we can find CF and EF. The next thing we want to do is to find the area of this yellow triangle. To do that, we need to realize that FG is the angle bisector for the triangle EFB. And we can apply angle bisector theorem, which says that the ratio of EG to BG is the same as the ratio of the side of this triangle EF to BF. Now the next thing we want to do is to realize that BG is BE minus EG. And now what we find is we know everything on the left, and what we don't know on the right is just EG. So we can solve this equation for EG and find EG. And now we're ready to calculate the area of the yellow triangle. It's a half of the height, EF, times the base, EG. Now let's find the area of the green triangle. First of all, notice that F is a centroid, is a point of intersection of medians. And because of that, the area of the triangle EFB equals to the area of the triangle DFC. Now, if you know this fact, good for you. If you don't, we're going to derive it right now. So here we have our triangle ABC, and we have two medians. All we care right now is BD and CE are medians, and F is the point of intersection of them. Now, if F is the centroid, and EF has a length A, in this case CF will have length 2A. Similar, if DF equals to B, FB should be 2B. If this angle F in the blue triangle is theta, in this case angle F in the gray triangle is also theta, because those are vertical angles and they're congruent. And now all we need to know is that the area of the triangle could be expressed via lengths of two sides and the angle between them. In fact, the area of any triangle is the product of two sides times sine of the angle between them times 1/2. And if we apply this formula to the blue triangle, we get this expression. If we apply the similar formula to the gray triangle, we get exactly the same expression. And that proves the fact that the blue and the gray triangles have the same area. And now what we're going to do, we're going to relate the area of the triangle EFB and the area of the yellow triangle. And we're also going to relate the area of the triangle DFC and the area of the green triangle. So let's start with the yellow triangle. The area of a triangle EFB is 1/2 height times the base. If we take the base as BE, the height we call it H. In this particular case, H is EF, but it doesn't really matter. What's important is that we can express the area of the triangle EFG in the same way, as half height times the base. And if base is EG, in this case, the height of this triangle is exactly the same H as the H in the triangle EFB. And now what we're going to do, we're going to divide one of these formulas by another one. In this case, we're going to get rid of H. And we get an expression for area of triangle EFB and the yellow triangle EFG. In a similar way, apply the same logic, we can relate area of DFC and the green triangle CFH. And since left-hand side we're told are the same, the right-hand sides also have to be the same. And from that we can get the area of the green triangle HFC. On the right-hand side we know everything except for CH. But we can find CH using angle bisector theorem in the same way as we found EG. If we look at the triangle DFC, FH is angle bisector. So we can apply angle bisector theorem that tells us that CH divided by DH is the same as CF divided by DF. And we know that DH is CD minus CH. So from here we can find CH, plug in this expression, and find the green area. And that is it.